So today we will start the colligative properties of solution. Colligative properties of solution. In the last class we have just discussed the four types of colligative properties of the solution. So now today we will discuss one by one. So the first colligative property is relative lowering in vapor pressure. Relative lowering in vapor pressure. Vapor pressure. So what is this relative lowering in vapor pressure? See, when you took the pure solvent and you vaporize this pure solvent, see, let us consider that this is the pure solvent, that is water, and when we vaporize this pure solvent we will get the 100% vapors. 100% vapors. Alright, now when we add some non-volatile solute in this pure solvent water, non-volatile solute, if we add the non-volatile solute in this pure solvent water, now the vapors will decrease. Why? Because this non-volatile solute molecules will adjust in the space between the water molecules or solvent molecules, which disturbs the solvent molecules to get vaporized. That is why the number of vapors will be decreased when we add the non-volatile solute in non-volatile solute in solvent. So the overall vapor pressure will be decreased. Alright. If we write this in a form of equation, how we can write? See, this is our pure solvent. So its vapor pressure will be P naught A. A stands for solvent. Okay. So let us consider for this pure solvent, the vapor pressure is P naught A. Now, when we add the non-volatile solute in this pure solvent, the pressure will become PA. Okay. Now, the change in partial pressure del PA will be equal to P naught A minus PA. How? Let us consider when the solvent was pure, the vapor that is formed is 100%. Now when we add some non-volatile solute in that solvent, the vapor will be decreased and let us consider it will become 80%. So now the vapors which is formed is decreased. So the change in vapor will become 100 minus 80, that is P naught A minus PA. So this is called the depression in vapor pressure or lowering in vapor pressure. This is the lowering in vapor pressure. Lowering in vapor pressure. Lowering in vapor pressure. Now from Raoult's law, we know that the vapor pressure in a solution, the vapor pressure in a solution of solvent or solute is equal to P naught A into XA. This is the vapor pressure formula according to the Raoult's law. Now we can substitute this PA value in this equation. So we will get del PA is equal to P naught A minus P naught A x A. Now you can take the common. So del PA will become equal to P naught A in bracket 1 minus x. Again we know that the sum of the mole fraction of solute and solvent is 1. XA plus XB is equal to 1, or we can write it like XB is equal to 1 minus XA. Now again we can substitute the value 1 minus XA is equal to XB. So we will get del PA is equal to P naught A into XB, or XB is equal to del PA upon P naught A. Again you can substitute the value of del PA. Del PA is equal to P naught A minus PA. So XB will become equal to P naught A minus PA upon P naught, where XB is the mole fraction of the solute. So this will be the derivation for relative lowering in vapor pressure. So this is our first colligative property. Alright. Now moving forward to the second colligative property, that is elevation in boiling point. Elevation in boiling point. Elevation in boiling point. Okay. So as we know that when we took the pure solvent, the boiling point will be the constant. Like if we take the pure water, the boiling point of pure water is 100 degrees Celsius. This is the pure solvent. Now when we add some non-volatile solute in pure solvent, like if we add the salt in pure solvent, this is solute plus solvent, and this is pure solvent. When we add the solute particle, non-volatile solute particle in pure solvent, the boiling point will increase. Let us consider it becomes 103 degrees Celsius. So this change in boiling point is called elevation in boiling point. This is because we are adding the non-volatile solute particles. Okay. Now, if we show this in graph, now let us consider the boiling point for pure solvent is T naught B. Naught stand for pure, and the boiling point for solution, that is solute plus solvent, is TB. Then the change in boiling point, that is the elevation in boiling point, will be equal to TB minus T naught B. Okay, the difference between that will be tell us about the change, that is the elevation in boiling point. Again write one more thing, this elevation in boiling point is directly proportional to the molality of the solution. Molality is what? Molality is the number of moles of solute present in 1 kilogram of solvent. So the more the number of solute will be there, the more elevation in boiling point will be there. Or when we remove this proportionality sign, we will get a constant, that is kb into m. So this kb is a constant which is called ebullioscopic constant. The value of kb is 0.52 for water, Kelvin, and the unit is Kelvin, kilogram per mole. Per mole. Okay. Now, if we draw the graph for elevation in boiling point, so you can write this formula in easy form is del TB is equal to KB into molality. Molality is what? Number of moles of solute upon weight of solvent. So this is how you can write the formula. Weight of solvent in kilogram. That should be in kilogram. Okay. Now if you draw the diagram for elevation in boiling point, the diagram will be like if we draw a diagram between vapor pressure and temperature. So like this is a atmospheric pressure 1 atm or 1.013 bar. This is for solvent or this is for solution. This is TB and this is T naught B, and the difference between them is del TB. This showing the temperature. So how you can define the elevation in boiling point? Elevation in boiling point. First of all, just write the definition for boiling point. Boiling point is what? Boiling point is that temperature at which the vapor pressure of liquid, the temperature at which the vapor pressure of liquid becomes equal to vapor pressure of atmosphere, that is 1 atm. So when the liquid's vapor pressure becomes equal to the vapor pressure of atmosphere, that is 1 atm, at that temperature we are that particular temperature is called the boiling point of that liquid. Here you can see we have taken the two, that this is the solvent and this is the solution, and we are drawing the graph between vapor pressure and temperature. Now you can see when we are increasing the temperature, the vapor pressure of solvent is increasing. At the same time, the vapor pressure of solution is also increasing. At a certain temperature, certain temperature, the vapor pressure of solvent becomes equal to the vapor pressure of 1 atm, that is the atmospheric pressure. And at again the same temperature, again if we still increasing the temperature at we will get the point at which the vapor pressure of solution become equal to the vapor pressure of atmosphere. So that temperature is called the boiling point of solvent, and this is the boiling point of the solution. Now we will get the solution before, because solution will get vaporized in lower temperature, and after that we will get the boiling point of solution, and the change between both is called the elevation in boiling point. So this is the all about elevation in boiling point. Okay. Okay. Now moving to the third colligative property, that is depression in freezing point. Depression in freezing point. Freezing. So first write the definition of freezing point. Freezing point is that temperature is that temperature at which the vapor pressure of vapor pressure of vapor pressure of solution, the vapor pressure of liquid becomes equal to vapor pressure of solid. Vapor pressure, vapor pressure of solid. So the temperature at which the vapor pressure of liquid becomes equal to the vapor pressure of solid, so that temperature is called the freezing point. So again you know that for pure water, the freezing point temperature for pure water is, that is T naught F, is 0 degrees Celsius. Pure water start freezing at 0 degree Celsius. This is pure solvent. Pure solvent. Now if we add some solute particles, non-volatile solute in this pure solvent, so it will become solution. Solution. Now the temperature, that is freezing point, will decreases, or it goes to the minus, let us consider -3 degrees. So this change in freezing point is called the depression in freezing point. You can write this change, that is del Tf will be equal to T naught F minus Tf. So this is the formula for depression in freezing point. Again you can write it del Tf equal to is directly proportional to K, directly proportional to molality, and when we remove this proportionality sign, so del Tf is equal to become Kf into m, and this Kf is called cryoscopic constant. Cryoscopic constant. Again when you draw the diagram for, so draw a figure. Again vapor pressure, against temperature. Okay, let us consider this is the vapor pressure of solid. So this will be the for solvent, pure solvent, and this will be for the solution. So we can make it like this. This is for solvent, and this is for solution. That is T naught F, and this will be TF. This is showing the temperature, and this will be the change in freezing point, that is del T. Okay, and this is for solid. So here you can see that when the vapor pressure of solvent touches the vapor pressure of solid, it becomes the freezing point of solvent, and when the vapor pressure of solution touches the vapor pressure of solid, it becomes the freezing point of solution. So this is how you can draw the diagram for depression in freezing point. So from the diagram you can see that we get the freezing point of solvent earlier. After that, if we continuously decreasing the temperature, we get the freezing point of solution as well. Now moving to the next colligative property, that is osmotic pressure. Osmotic pressure. First of all, you have to understand what is osmosis. Osmosis. So osmosis is a natural process, that is the flow of solvent from flow of solvent molecules solvent molecules from lower density to higher density, lower density to higher density, that is called osmosis. That is called osmosis. Flow of solvent molecules from lower density solution to higher density solution, that is called osmosis. Let us consider, if you take a tank and separate that tank by a semi-permeable membrane SPM, which allows only solvent molecule to pass, and in a tank one time pour that tank by pure solvent, pour that tank, that is pure solvent, and another side put the sea water, that is high density solution. This is your sea water. Okay, we have taken a tank and divide that tank by a semi-permeable membrane which allows only solvent molecule to pass. So what will happen here? Here one side is lower density solution, that is pure solvent, another side is a higher density solution, that is seawater. Now the pure solvent molecule will start moving toward the higher density solution, that is seawater. So this process of moving solvent molecule from lower density to the higher density is called osmosis. So this is the natural process. Now, if we apply a pressure from higher density sides solution, okay. Now, if we apply a pressure on higher density side, that is sea water, we will reach at that point when the moving of solvent molecule will stops. If we increase the pressure in high density side, we will come to the point at which the movement of solvent molecule stops. So you can write it here, the pressure at which the movement of solvent molecules the movement of solvent molecules stops toward higher density solution, that particular pressure that particular pressure is called osmotic pressure. Osmotic. So osmotic pressure is that pressure which stops the process of osmosis, or which stops the osmosis. The pressure which stops the osmosis is called osmotic pressure. Alright. So you can write it like, when the external pressure, osmotic pressure is represented by pi symbol. When the external pressure PEXT is equal to pi, osmotic pressure, the osmosis will happen, or osmosis will take place. Osmosis will take place when osmotic pressure is greater than external. When P external is greater than pi, the osmosis will take place. When pi is greater than P external, then wait. When pi is equal to, then osmosis stops. Osmosis stops. And when P external is greater than pi, then reverse osmosis will take place. Reverse osmosis take place. Now, what is reverse osmosis? When we apply the pressure more than osmotic pressure, like if we keep increasing the pressure from the solution side or higher density side, if we keep increasing the pressure, a pressure will, and we pass out the osmotic pressure. So what will happen? the solvent molecules which are present at the solution side, they will start moving toward the lower density side, that is pure solvent side. So this reverse movement of solvent molecules is called the reverse osmosis. So reverse osmosis will take place when the external pressure applied is greater than to the osmotic pressure. Osmotic pressure is that pressure at which the osmosis process stops. Again, if we continuously increasing the external pressure, then a point will reach when the solvent molecules will start moving toward the lower density side. This is called the reverse osmosis. Okay, one more thing. This osmotic pressure is directly proportional to the concentration of the solution, and this osmotic pressure is also directly proportional to the temperature. So if we write both them, so we can write it like pi directly proportional to the C into T. And if we remove this proportionality sign, so we will get pi is equal to C into R into T, where R is gas constant, C is concentration of the solution, and T the temperature. So R is this constant, what? Constant, gas constant. R is gas. The value of R is 0.082 atm liter per mole. Okay, R Pv is equal to NR. R is what? atm liter per mole Kelvin per mole. So this is the value of R for atmospheric pressure. So this is all about osmotic pressure and reverse osmosis. Reverse osmosis is also called RO in short. In our houses also we use the RO water filter, which works on the principle of reverse osmosis. Wait, one more correction is there. This is pi is greater than fixed.